Hey guys, and welcome to another video in my series of videos on electromagnetism. In this video, second video, we're going to carry on with some of the preliminary maths. There won't be a huge amount more, you'll be pleased to know. But this time we're going to have a look at some of the calculus that's going to be needed for electromagnetism. Of course, calculus is quite an important part of lots of areas of physics, so hopefully some of this stuff should be fairly familiar to you. Let's get right to it. So the first thing I'm going to have a look at, I'm going to quickly go through coordinate systems. You guys are probably familiar with some of these concepts already. Obviously in electromagnetism you're going to get given some kind of physical problem, and it's very often easy to know in what sort of coordinate system you're going to be working in, because if you know the coordinate system you can actually make the problem a lot clearer. And in physics we mainly use three types of coordinate system. They're by far the most common. Of course you can have any coordinate system, but there are three types. There is the Cartesian, the cylindrical, and spherical. Now probably the one you're most familiar with is the Cartesian. This is the simple kind of X, Y and Z representation that you've probably seen. In actual fact, many problems won't be in 3D. They'll probably only be in 2D. So in that case you probably only have X and Y. The Z only comes into play if you've got a 3D problem. So that's the Cartesian. The cylindrical, probably if it helps if I draw these out. The cylindrical coordinate system is based on, it's similar, probably most similar to the Cartesian, except the XY plane, which I'm going to sort of draw as like the flat base. Here's the Z-axis, and this is the XY plane. So I'll just label that. So here's the Z-axis. The y-axis I normally do going into the paper. That's going to be the convention that I'm going to use. I know that sometimes you can rotate it slightly, but this is the convention that I will be using. So you've got the xy plane, and you've got the z-axis that's pointing vertically upwards. Now in cylindrical, you basically, instead of having an xy coordinate, you have a radial coordinate from the z-axis, so how far away something is from the z-axis, and I'm going to call that r. You might see it being called rho in some cases, but I'm going to be calling this distance r. And of course from Pythagoras you guys can see that r is the square root of x squared plus y squared, so it's simply the distance away from the z-axis right here, which is the axis at which both x and y are 0. So you got r, but of course you're going to have to define another variable, which is the angle, the polar angle theta. And theta we normally take from being the angle from the x-axis turning counterclockwise. So this is the angle theta, and you can work out theta. It's the arctangent of x over y. And of course you guys are probably familiar with the transforms, that of course x equals r times the cosine of theta and y equals r times the sine of theta. So that is theta. You might hear this being called phi sometimes. It just depends on the problem, but just make sure you know which is which. I'm just going to use r theta, and of course in cylindrical the z coordinate doesn't change from Cartesian, it's just simply the height above the xy plane. So that's cylindrical, and we have the three variables r, theta and z. So that's cylindrical. What about spherical? Well, spherical is probably kind of the hardest to visualize really, but you have kind of the origin, and of course you have, there's not really any kind of axes in spherical. It's kind of mainly for points which have what's called spherical symmetry. So there are loads of problems which the only coordinate of relevance is going to be the distance between the origin here and where this point is right here. So in problems which have that property. We call them spherically symmetric, and it's helpful to use a spherical coordinate system. So this distance right here between the origin and this point, I'm going to call r. Now, it's not the same as this r right here. This r is actually the square root of all three coordinates. If you want to transform between coordinate systems, this is actually going to be the square root of x squared plus y squared plus z squared. So this is r in spherical, this is r in cylindrical. Not the same r. And in spherical, you're going to have two angles. They're commonly called theta and phi. And they're typically a bit like latitude and longitude, or azimuth and latitude, if you want. The angle phi I normally take as the kind of longitude. So if you imagine sort of like a globe, this is kind of like the equator of the globe, and here's our globe right here, and this is kind of like the mid plane right here. This plane right here. The angle between the x-axis and wherever this point is phi. Now this is actually kind of the same as this angle theta right here, but typically it's called phi, and that's the azimuth angle. So phi obviously goes between 0 and 2 pi. Should have probably mentioned earlier, theta here goes between 0 and 2 pi. And theta is the other angle, which is the latitude angle, and that basically describes how far from kind of the North Pole you are. So this is kind of the point where theta is 0. That's, if you like, the North Pole, and theta is 90 is the equator. So all around the equator, theta is 90, or pi over 2 radians, I should say. I should be using radians. And right here at the bottom, theta is pi radians. So I know that the notation isn't great. Obviously, cylindrical and spherical have somewhat conflicting things. So theta in cylindrical is actually the same as phi in spherical, whereas theta in spherical is often different. But I'm only going by what the convention is and what I've seen in most problems. And this is kind of the convention that most physicists tend to use in my experience. So that's basically an introduction to the different coordinate systems. You have different like unit vectors and stuff in coordinate systems. Typically you'd get given them. You can derive them. It's quite complicated. You can derive them using the chain rule. But typically you get given those sorts of things. A couple of quite useful ones that I've found to be quite useful is the unit vector r hat in spherical is sine theta cos phi x hat plus sine theta sine phi y hat plus cos theta z hat. That's quite a useful conversion that you can use from going from spherical unit vector to Cartesian unit vector. There's also another quite useful one between going from r hat and z hat. The z hat unit vector is r hat cos theta plus theta hat, minus theta hat sine theta. So that's quite a useful one as well. There are a couple of other useful ones, but typically you get given these, so I wouldn't worry too much about them. So yeah, that's just a basic introduction to coordinate systems. So next we're going to talk about partial differentiation. And so to do this, I'm going to suppose I have some function f. And this function is actually not only going to be a function of one variable, but it's actually going to be of two variables, x and y. Now, you guys are probably familiar with how to take a partial derivative. So the way we represent that is by using these curly d's right here. We call them debas. And this basically means the partial derivative of f with respect to x. And sometimes we might put a little thing here just saying you're keeping y constant. So quick example, if f of xy is, I don't know, 3x squared y, then differentiating f with respect to x but treating y as a constant will just literally give you 6xy. So I hope you can see that. We've kind of left the y alone, but the x has been differentiated to give that. So that's just a quick example of what a partial derivative is. And obviously you could do it the other way around. You could have debit f by debit y holding x constant, and to do that, that's just 3x squared, and the y just turns into a 1. So again, those are the two different partial derivatives. And to get the full derivative from the partial derivative of x, so the full derivative is big D, normal D, f. This can be expressed as partial f by partial x holding y constant times a change in dx, plus partial f by partial y holding x constant times dy. So it's basically you're summing the contributions from each derivative. So that's how you get the full derivative in terms of dx and dy. So you evaluate the partial derivatives. A couple of other things. There is a couple of quite useful theorems. I'm not going to write them out. I'm going to just put them up on screen right now. There is the reciprocal theorem. That's quite an obvious one. You basically can just invert the derivative. The reciprocity theorem is a little bit more complicated, and it basically shows that the product of the three differentials, if you interchange the variables cyclically, is equal to -1. That's quite useful. You don't use it a huge amount in electromagnetism. In fact, you kind of use it a lot in thermodynamics. That's the only real place I've seen it being used. So, but there they are in case you need them. I hope you guys are familiar with the chain rule. The chain rule is going to be quite an important thing, where it's important throughout all of physics, really, the chain rule. And that basically says that, say you want to differentiate this function. So you have some function y equals u, but u is like a function of x. And so say you've got something like, I don't know, log of 3x. So say you have some kind of composite function. Then to evaluate what the derivative of y with respect to x is, dy by dx is equal to dy by du times du by dx. So if we let 3x equal u, so y equals ln of u. Yeah, sorry, I wasn't quite right on that. I'm basically saying that the function y is a function of u, but u in itself is a function of x. That's what I meant to say. Sorry about that. That was a little bit unclear of me earlier. I hope you guys can see what I mean. So y is a function of u, but u in and of itself is a function of x. So as you can see, this is your u right here, 3x. So dy by dx equals dy by du times du by dx. So in this case, dy by du, well, we've got ln of u. Derivative of ln is just 1 over u times du dx, which is, well, u is just 3x, so therefore du by dx is just simply 3. We can substitute back in what u is, which is 3x, and so we just get 1 over x again. So that's actually quite a neat property of log functions. It doesn't really matter what the argument is, you will always get a derivative of 1 over x if you differentiate a log function. So that's a chain rule. I'll highlight that. It's quite important. You're also going to get the product rule. That's again pretty important. The product rule is basically differentiating, say you have a function y equals u of x times v of x. These are both functions, so let's say you have, I don't know, sine x e to the minus 3x, so these are both functions of x. Then the derivative of y with respect to x is equal to the second function times du by dx plus the first function times the derivative of the second function, which in this case is going to be e to the minus 3x times cos x plus u, which is sine x, times the derivative of the second function, which is minus 3e to the minus 3x. And that last derivative I kind of did automatically, the chain rule. So I hope you can see why, how I got from there to there. Again, you guys are probably familiar with this. So yeah, that's the product rule. There's also the quotient rule. That's just kind of the same as the product rule. So next up, I'm going to talk about line integrals. So this may be something that you're maybe a little bit less familiar with. It's kind of a little bit of a weird thing to get to grips with at first. Now, the best way to explain it is by sort of explaining it visually. And I'm kind of just going to explain what integration actually is. So say you've got y and x right here. So you've got some kind of set of axes, y and x, and here's a curve. So here's some kind of arbitrary curve. And this curve is described by the function y of x. So it could be anything. We don't know what it is, just some kind of arbitrary curve. Now what we do when we're integrating is we're actually finding the area in between 2 points. So say we want to find the area between this point here, which is at x1, and this point here, which is at x2. So we want to find what this area right here is between these 2 points. And the way we do that is by integration. So to find the area, we simply do the integral between x1 and x2 of the function y of x in between these two limits, and we integrate it with respect to dx. So that is the area of that curve. But what if we don't integrate along the x-axis? What if we're given a function which we have to integrate along a line right here? So as you can see, we're doing the integral along this x-axis right here. We're taking lots and lots of different summations along the x-axis, but now I'm kind of saying, what if we do our integration along this curve right here? So instead of summing along the x-axis, we're actually summing along this curve right here. Well, that kind of sounds a little bit weird, you know. Why are we doing that? That sounds a little bit odd. So the best way to do it is I'm going to explain it with an example right here. So what I'm going to do is I'm going to consider that we have a wire. This is some kind of metal wire right here. Now, this metal wire, for some reason, it has an unusual property in that it doesn't have a constant mass density. Now I'm going to define this thing called mass density m as being the kind of mass per unit length. So it's going to have units kilograms per meter. But say we have this funny wire which kind of doesn't have a constant mass. So basically what that means is that it's going to have more mass concentrated here than it will do in, say, well, there's a little gap there, for example, that I accidentally happened to draw, but turns out to be quite nice for that example. So you've got this weird kind of wire like this. This mass density varies as a function of x and y right here. Now, the question is, how do we calculate not only its length, but what about its mass as well? Well, for the moment, let's kind of forget about the mass. We need to figure out some way of calculating the length of this curve right here. So how are we going to do that? Well, what we can do is we're going to zoom in to this tiny part of the wire. Now, if we zoom in, we're basically going to see that the wire is virtually straight. It's not going to curve at all. And let's take 2 points on this wire. We've got point 1 over here and point 2 over here. Now, this is going to be a very, very, very zoomed up representation. So these distances are going to be very, very small compared to the length of this wire. So right here, of course, here's our y-axis, here's our x-axis. So this distance right here, this kind of distance along here, we're going to kind of assume that it's straight. If you zoom up infinitely close, it will be straight. And we're going to call this delta S right here. So this distance along, the actual distance along the curve is delta S. But along this line right here, well, this is just parallel to the x-axis, so this is going to be some very small change in x, and this distance right up here is going to be a change in y. So I hope you guys can see that that from Pythagoras, that delta S is simply the square root of delta x squared plus delta y squared. So this is what happens when we've really zoomed in to this wire. And the wire isn't curved when we're infinitely zoomed in. That's kind of the point. And so we get this right here. Now, if we take the infinitesimal limit of this, so we kind of go infinitely, zoom infinitely in on this wire, then we actually get the differential ds is equal to dx squared plus dy squared, all to the square root, or all to the power of 1/2. So that is what ds is. And so this is kind of exactly the same as what I was talking about over here. You know, ds would be some kind of infinitesimal change along this curve right here, whereas dx, of course, is our familiar change along the x-axis, which is what we're kind of used to integrating in this relation right here. So that's really good. We could have a relationship between integrating along a curve and integrating along the x-axis. And so what I can actually do is I can, in fact, do a little bit of rearrangings and get that ds is, if I divide everything in the square root by dx squared. So what am I going to get? I'm going to get dx squared over dx squared plus dy squared over dx squared. So if I've divided everything in the square root by dx squared, then I must times everything outside the square root by dx, of course. So I've done no harm to this equation. I've just multiplied the outside by the same thing I've divided the inside by. So no harm has been done. And as you can see, this kind of simplifies a little bit. So you're going to simply get 1 plus dy squared over dx squared is simply the same as dy by dx all squared multiplied by dx. So that's really good. That's really helpful. We have ds in terms of dx, and we know how to evaluate dx because that's what we do normally. But if we know y is a function of x, so we know the equation of this curve or this piece of y, if we know the equation, then we can simply convert between a line integral to a normal type of integral that we are used to being able to solve. So how do we get the whole length of this curve? Well, to get the whole length, we simply have to add together all of the little lengths. So we do the integral of ds to get the whole length, L, of this curve, which is the first thing we're trying to find out, remember. So what we normally do is we simply write a little c just to say that we're integrating over a curve. And of course, we know what ds is. We just worked it out. And we know that it is square root of 1 plus dy by dx all squared times dx. So if we know the equation of that curve, then we can evaluate what dy dx is. So if the curve was sine x, dy dx would be cos x, dy dx all squared would be cos squared x. Then you have 1 plus cos squared x under the square root. There's probably some trig identity there, who knows? And yeah, you basically, happy days, you'd be able to evaluate it. So that's how you'd work out the length if you knew what y is of a function of x. But what about the mass? Well, mass is no real difference really. You know, the total mass of the ym is going to be the mass per unit length, which of course we said was m xy, multiplied by the length. Of course, it's not that simple because the mass per unit length it changes as a function of x and y, and so that basically means that it has to be integrated for every small step. So that's not quite right. What we actually have to do is we have to integrate the mass function, the mass density function, over the curve right here. So we can't simply just multiply it by L because the mass function depends on x and y. So again, and then we can just simply substitute in what ds is. So we have m of x and y multiplied by the square root of 1 plus dy dx all squared times dx. And of course then you can substitute in limits of what x is, and so what the x limits would be is, well, they would be simply whatever the x position is right here to whatever the x position is right here, which is super helpful because then we can simply just do a straight integral along x and Bob's your uncle. So what we've technically done right here is we've done a thing called parameterization. We've parameterized this curve. We've got it from this kind of awkward thing to something that we know how to handle, and that that has a lot of implications. It's very useful for when talking about the work being done by a force. You find that the work being done by a force is the integral of the force over a path, dl. dl is exactly the same as ds, it's just normally written as dl because physicists can't make up their mind as to what to call things, basically. Of course, these are actually vectors, and so important to put little vector hats on them, so that's what I'm going to do. But this dl, again, you can get it in terms of x and y, which is something that you're much more familiar with. So I hope that makes sense. I'll include a couple of examples or something in the description, or if I'm on Skillshare, then I'll include a couple of examples on how to do this because it's very useful to practice this sort of thing. Quite an important concept. So yeah. So one other thing to mention about line integrals is that they have quite a good physical resemblance to what's called conservative forces. Now, a lot of the time you deal with conservative forces in electromagnetism. Now, the electric field happens to turn out to be a conservative force. So just a quick example, say you've got an electric field right here. Now, say you wanted to move a charge, we're going to get into what all this is a bit later on, all the way from this point here to this point here. So of course the electric field lines run from positive to negative, and so say we have a negative charge. Now what we're going to have to do is we're actually going to have to put in some work in order to get it to over here, because of course like charges repel. This negative charge isn't going to want to go this way, it's going to want to go this way. So if we want it to go this way, then we're going to have to put in some work. So we could, to be honest, we could take any path we wanted to, really. But let's say we go along here. Let's say we take this route right here. So we take this route, we can calculate what the work is using the integral. If we know what this equation of the curve is, you may know what it is, you may be given it, you never know. And then you can calculate the total amount of work done and needed to moving the charge from here to here. So that's all good, but what if we decide to go, I don't know, what if we decide what if we're a little bit high or something and we don't quite know what we're doing, and we decide to go this way? And so what is the work done if we go along this route? Well, it turns out that the work done if you go along this route in an electric field is exactly the same as the work done going along this route. So the work done going along the blue path is exactly the same as the work done being if you go along the red path. And this is true of the electric field. It's also true of a gravitational field. It's not true of friction. That is a path-dependent variable. And so therefore that is not true. But with the electric field, the work done is exactly the same. And that basically means that it is called a conservative force. A conservative force is one in which the work done is path independent. So that is just a quick point to note. Quite an important concept that. So yeah. And the last thing I was going to talk about is kind of an extension to line integrals. It's basically the two-dimensional equivalent of a line integral, and that's a surface integral. So now we're going to be in 3D space, and this is going to have our x-axis right here, our y-axis here, our z-axis right here. And instead of having a line, we're going to have a surface, which is basically, it's not a solid shape. It's kind of like, if you imagine like a sort of roof or something, it's going to be some kind of surface. It may have the odd hill or something, you never quite know. So you're going to have some kind of surface right here. Typically in electrostatics, you'll be given fairly simple surfaces, like sort of cylindrical surfaces and spherical surfaces. So that basically in practice means that the integration is a lot easier to do. But say, for the purposes of this example, I'm just going to talk about a arbitrary surface right here, and we're going to call this arbitrary surface S right here. So this is an arbitrary surface in space. Now, what if we wanted to work out the mass of this surface, similar to how we wanted to work out the mass of the line? Well, say we get given this same kind of density function, m of x and y. So this density function is going to be a function of both x and y. So similar to how in 1D that we said, to get the total mass of the wire, we multiplied the linear density by each infinitesimal point. Well, the same thing, we're going to do exactly the same thing in this case. So to get the total, mass of the wire, we're going to do an integral of all the little masses of the wire. And the little masses of the wire, we just kind of said, was this kind of mass density function multiplied by the, instead of dl, which is the line density, which is the line element, we're going to have a surface element, ds, right here. So this is basically the two-dimensional equivalent of what we just said earlier. So that is kind of how to get the total mass if you are given the mass density function and you know the equation of the surface S right here. Now ds is an area element. So the expression for ds is going to be a little bit more complicated than that for just a line element. So it's going to be dependent on various different coordinates. It's going to be dependent on the coordinate system that you're in. So here we've got our kind of surface, and the thing is, you have to imagine that it's some kind of really bumpy random surface right here. What we want to do is we want to evaluate it over the xy plane, similar to how earlier we wanted to evaluate our integral over the x-axis. In this case, we want to evaluate it over the xy plane. So we take our kind of bumpy surface right here. So let's take some kind of element here, and what we do is we kind of almost project this down onto the surface right here. We project this down onto the xy plane, similar to how we projected this, little line element onto the x-axis. In this case, we're projecting some small surface element onto the xy plane. Now, I'm not going to show this because it's quite a complicated derivation, but to get ds in terms of dx and dy for any general surface, then ds is equal to the square root of 1 plus grad of z all squared times dx by dy. And I should have mentioned here, this surface right here, this surface is defined as z as a function of x and y. Probably should have mentioned that before. So say you have, some equation, z equals 30x squared minus sine x y. So z is defined in terms of x and y. Z is a function of x and y, and so if you're given that, then you can evaluate what grad of z all squared is, and yeah, that's how you get from ds to dx dy. And I hope you guys can kind of see that this again is kind of equivalent to this equation right here. So instead of just simply dy by dx, you have grad of z all squared. Now, of course, I've kind of only taken the magnitude of the gradient. Obviously, I said in the last video that gradient is, in fact, a vector quantity, but in this case, you only take the magnitude of it. So if I was to really expand this out, then you get the square root of 1 plus dz by dx all squared plus dz by dy all squared times dx dy. So that's what you get if you expanded it out and simply taken the square magnitude of the gradient of z. So that is how you would evaluate ds in terms of z if you knew z as a function of x and y. And so I hope you guys can see that if you know what ds is, then you can simply insert this into here, and if you multiply it by the mass density function, then you'll be able to obtain the total mass of this whole area right here, and happy days, really. That is the total mass, and we do it in a way in which we know how to deal. And again, I encourage you guys to have a look through some various examples that I've included. So yeah. And just to end things off, there's a couple of surface elements, ds, that you guys are probably going to need to know quite well. These are a couple of very specific cases of what ds is, and I'm not going to derive them. I'm just going to state the final result. So say you have kind of a surface in simple Cartesian space. So say you have a surface along the xy plane. So you have this surface right here. This surface is simply dx multiplied by dy. Quite simple in Cartesian. So ds in Cartesian is dx times dy. So that's a simple case. What if you're looking at a circular surface right here? So say you have a circular surface and you wanted to evaluate what the small area is along the surface. And so say you wanted to go from, say, this point here to this point here, then you're adding extra surface right here. ds in this case is r dr d theta right here. So instead of just simply dx dy, because of the geometry, the surface area of a circle is r dr d theta, and so that's if you're integrating all across this 2D circular surface right here. So that's the case for a circle. What about a cylindrical surface? So with the cylindrical surface, you have obviously something that looks a little bit like this. And what you'd normally be doing for this type of surface is you'll be evaluating it upwards right here. You'd be evaluating it upwards, and you'd also be evaluating it around this surface right here. So you'd actually be evaluating it along the z-axis and along well, what's this axis right here? Well, it's going to be the theta axis, if you like. I don't know if you really call them axes, but for sort of this kind of geometry. But yeah, so the surface area element for a cylindrical surface, something a bit like this, is r d theta dz. So as you can see, in this case, we're not actually evaluating across r at all. We're actually only evaluating across theta and z. So if you actually draw the little element, you can kind of see why. There's no, it's a constant radius r from this kind of center of the cylinder. So yeah, I hope you guys can see what I mean by that. And lastly, this is also a pretty important one, a spherical surface right here. So we have some spherical surface, some kind of spherical shell. You're going to be doing a lot of these integrals, I can tell you that. So it's important to know the area element. So ds for a sphere is r squared sine theta d theta d phi right here. So again, similar to this kind of surface right here, we're not actually integrating across r, because if you think about a spherical shell, it's going to be a constant distance from the origin. If you think about a sphere, and just the sort of outer shell of the sphere, it's all going to have a constant radius. And so, yeah, that is the surface area element for evaluating it for a sphere. So that is kind of all I want to talk about in this recording. I know I've probably gone through quite a lot. I've kind of just wanted to summarize the maths that you typically be using in electromagnetism. There's quite a lot of maths. There's going to be probably one more video on the maths, and then after which we'll be ready to start on the proper physics stuff in electromagnetism. So not too long now. But yeah, I hope that all made sense. I know I probably went quite quickly. Hopefully you guys know most of that stuff, at least to some extent, and this is kind of just mainly revision for you. So yeah, till next time, I'll see you guys in the next